it off. And you are the that's not the right one. You are the immersible IoT sensors from Stanford University. You have a cloud-based project that keeps your results grounded in reality with data gathered by unique gallium arsenide transistor-based sensor platforms that are interfaced with nanoporous membranes. These sensors purport to be more resilient in extreme conditions and have a 5x greater sensitivity compared to the state-of-the-art, and leverage a unique twist on LoRa communication network for transmitting sensor results. It's up to you guys. Thank you.
Good afternoon. One of the largest problems the world of aqua faces is harmful algae blooms. These algae blooms suck up all the oxygen available in your water sources, killing off large parts of your aquatic life, and poses a huge threat today globally in the United States and rest of the world. This is predominantly caused by three pollutants: ammonia, nitrates, and phosphates. These pollutants enter through your agricultural runoff and from your sewage treatment plants. Today, to actively mitigate this, we require a series of solutions. But the problem is in the billions of dollars. We lose up to $2.2 billion in the United States alone for remediation for eutrophication, one such problem that harmful algae blooms cause. This is a problem faced by my own home country in India, in Malaysia, in New Zealand, around the world. What we need is an IoT-based solution where we can produce commercial ammonia sensors to be able to detect this. We have nitrate sensors, we have phosphate sensors, pH, temperature. The one sensor that we lack today is ammonia. The state-of-the-art ammonia sensor and the way ammonia is currently measured requires a field research scientist to often go in, collect a sample of water, add a chemical reagent, shine a laser through it, and then based on the chemical absorption, we get to know what is the ammonia levels. Now, this is not particularly deployable. You cannot do large-scale monitoring. And if you want to predict and potentially mitigate harmful algae blooms before they become a problem, you need to be able to collect live data across thousands of miles and thousands of kilometers in your waterways. We need a low-cost immersible ammonia sensor and an IoT platform that is cost-effective and can be proven economical for such a solution. To that end, we at Stanford have developed a novel sensor payload that does precisely that. We can detect ammonia, and then we have tied it in with our IoT platform that was developed for NASA. Using the two together, we can not only interface with different sensors, but we are able to collect this technology. We are an interdisciplinary team at Stanford taking the work done by three professors: Professor Debbie Sineski's microelectronics for harsh environments, Professor Zach Manchester's robotics and microsatellite platforms, and Professor Tarpe's expertise in water and chemical engineering. We have combined technology and transferred them from multiple different places to try and solve this one large pressing issue. I am Anand Lalwani, and this is Max Holliday. We are PhD students at Stanford actively trying to solve this problem. Our IoT platform is unique. This was a microsatellite that Max Holliday and Zach Manchester developed and deployed earlier this year in February through the ISS. It has flown in orbit, and we have been able to prove that it can survive the conditions of space. Because we have built it up from ground up, we can interface any commercial sensor we like, and it is tiny. It's 3 centimeters by 3 centimeters. We have developed a patent-pending ammonia sensor. This ammonia sensor builds on the work done by Professor Tarpe, where we can get incredibly high selectivity. We can take out ammonia from the river water and only have that in the third chamber. The problem is the third chamber has sulfuric acid. Now, if you want to monitor anything in sulfuric acid for extended periods of time, your silicon-based sensors do not work. That is where Professor Debbie Sineski's gallium nitride sensors come into play. So this gallium nitride sensor can survive incredibly harsh conditions. It is chemically very resilient. And we have fabricated this at Stanford NanoFab using lithography and plasma etching, et cetera, to be able to build that. The gallium nitride sensor builds on the work done in the world of touchscreen mobile phones. So all of your touchscreen mobile phones have fantastic capacitive sensing technologies. We transfer that over to the world of chemical sensing, and as far as we know, we are the first to ever get capacitive sensing into the world of chemical sensing. This allows us 5x greater sensitivity in ammonia detection than any state-of-the-art sensor. Here we have shown a small experiment where we added in a tiny drop of ammonia into our sulfuric acid chamber, and we saw a huge spike in the capacitance that is present over there. To survive for long periods of time, we have been able to produce an incredible battery life. Just on one Panasonic coin cell sensor, we can last easily up to 3 years and north of that. Although we have the ability to add in solar, and you will very quickly see in our demo that we have pads for solar that are available, we do not need it. And for cost reduction purposes, we decided to just go ahead with this battery life. Since our technology has been built from ground up, it's completely configurable. We can decide when we want to turn it on, we can go into deep sleep, and we can take as many measurements we like. At the moment, we get 3 years of lifetime with measuring every single hour. This allows us to create incredibly rich data sets. We live in the world of artificial intelligence and machine learning, but it is only as good as the data that we can provide it. There is tremendous resources of data on our online platforms. Facebook knows exactly what we are doing, and Google can track us tremendously. One thing we do not have is good data about our environment, about our water sources. And being able to collect this, put it in a cloud-based format, provides us data sets that are rich enough that we can derive insights. And these insights can then be given to local agencies, to government bodies, and to industries to proactively monitor and then take action. Before a problem becomes a problem, we can go in and stop it, thus saving millions of dollars. We are economical. Our entire system, from our IoT platform to our ammonia sensor, costs less than $29. And we can easily interface with any other commercial sensor we like. This has piqued the interest of different industries. Vishwaraj is a leading water treatment facility in India that is very interested in our technology, and we have already signed a pilot deal with H2OK Innovations. It's a startup not far from here in Boston that is trying to do water-based IoT. We have demonstrated reliability. Our systems have literally flown in space. NASA has tested them in the harshest of conditions possible, including dipping it into liquid nitrogen for weeks at end. Gallium nitride is known to survive the worst of conditions possible, far better than silicon can ever think of. And based on that, we'll now do a quick demo and implementation.
Thank you, Anand. So that covered a lot of hardware, and we all know live demos are fun. So let's start with a live demo. If the judges would be so kind to open up those envelopes on their tables. Sorry, Daniel. You'll get one afterwards.
That's okay.
So what I'm holding in my hands is the entire platform that we just talked about, but it starts with that little microsatellite that lives in this top buoy part that I'm holding in my hand. Now, in all of your envelopes is the same microsatellite that's yours to keep, take home, use. It's a dev board. It's quite fun. And that's what we're using to drive all the electronics behind the sensor platform. It's connected through an interconnect here that talks to the sensor payload that is a variable depth sensor payload that allows you to measure whether it be ammonia, pH, temperature. There's a bunch of sensors housed here that we use, and we can set the depth in whatever water system it's in. Now, for communication, we've already heard a lot today about LoRa. What's unique about our LoRa implementation is, so we're creating a mesh network. All of the nodes are peer-to-peer. They talk to each other. If a peer is lost in the mesh, it will store packets until internal flash is filled, and then it will push out the latest. But what's really unique about our LoRa is that we're using a newer chipset from Semtech that lets us leverage a time-of-flight ranging capability. And what this lets us do is we can measure the round-trip time it takes for packets to go between nodes. And the end result is we get positional accuracy of our nodes with less than a meter. And so we're achieving this every time we're communicating. And so to say that we have a 3-year lifetime, something that we've measured using a source meter, integrating over hundreds of wake-sleep cycles, that 3-year lifetime is with a positional accuracy that you would not even be able to achieve with a GPS, let alone cold starting. The power draw with a GPS would be significant. So we're getting the positional accuracy necessary, and we're coupling that with the data-driven sensor node that lets us implement the types of sensors that we'd like to see. So you have in your hands the sprites for you to take home. Now let me hand out some other demos. I'm going to try to distribute these. So the one I just handed off to the right here to Daniel is a sensor node that doesn't have the ammonia sensor attached to it, but it's collecting temperature data from the microcontroller it's just an on-die temperature sensor, and it's relaying that over to a gateway. So along the way, this new Semtech chip, the various things that we've built, they're all open source, they're all on GitHub. There weren't libraries for these chipsets yet in Arduino and CircuitPython, so we wrote those and published those to the community. All this instigated, right, by the need of trying to come up with this challenge for the Keysight competition. So in my hand here is the gateway. It's what this sensor node that I'm passing around is talking to, and it's uploading data real time to a dashboard, much like you've seen here today. The dashboard allows us to view the data real time. The green here on the bottom, this green plot that we see, green and blue, is the temperature reading from the sensor that's being passed around here with the little LiPo battery attached to it. The nice part is that if you notice, there's no solar cells on this deployable on our platform. And by not needing solar, we're doing a couple things. We already have the 3-year lifetime that can be tuned depending on how often you're sampling. By eliminating the need of solar, we reduce costs, we reduce the manufacturing challenges, and we also enable the sensor to work in a wide variety of weather. We don't need to have solar in order to operate. And if there's an application that really does need that power draw, we have the pads there on the board. We can populate it and energy harvest if need be. So with that, it covers sort of the demo and what data we're doing. And I'll hand it back over to Anand.
So today, you can help us achieve our goals. The $100,000 from Keysight will go into 2 major ways. The first, we require the B1505A from Keysight. It's a power device analyzer that will help us more accurately measure our power draw.
We had to use a Keithley to do the power source measurements. Just FYI.
Yes. It will help us characterize also and precisely measure the capacitance which we require for our sensing. The remaining $50,000 will predominantly go into scaling and manufacturing of our components, accelerated age testing, and deploying it and field testing it in the Mississippi. We genuinely do want to try and collect data and be able to accurately predict the possibility of harmful algae blooms in the Gulf of Mexico. It is a real-world problem, and you can help us solve it by saving millions of dollars. We are a Stanford interdisciplinary team that is trying to find data-driven solutions to global aquatic problems. Thank you.
All right, let's hear it for the Stanford team. I'm sure we have lots of questions, but I want to first address that it's gallium arsenide and